So moving on, welcome to Chapter 7. And what this little PowerPoint is supposed to do is just zip you through the key content in 7.1 and 7.2, which, by the way, doesn't mean that you shouldn't read it, and especially pay attention to the diagrams and all the captions and all that good stuff in there. But I just want to touch on some of the highlights here. What you should be able to do by the time you get to the end of this presentation is answer questions like the following. Pretty much all of them based on the periodic table. When you're working through all of the chemistry unit, make sure you have a data booklet handy with your periodic table in it. In this case, just so your brain is already kind of pre-processing the information, this kind of information in the presentation is going to allow you to answer questions like this. So if you look at, say, columns, where are we here? Let's get our little pen going. In color, green, sure. So if you look at the columns, column 1, column 2, 3, 4, 5, all the way through 18 being the noble gases, you should be able to look at those columns and determine how many electrons each element would lose or gain to have the same number of electrons as its nearest noble gas. So in other words, group 1, lithium, how many electrons does it have to lose to become like its nearest noble gas, which would be, of course, neon. Group 2, how many electrons would magnesium have to lose to become like its nearest noble gas, which in this case would be argon. You get the point. What you're going to notice about each of these families, and again, the families are the vertical columns. Each of them has certain characteristics in common, and hopefully you can intuitively come to realize what that characteristic is. And what that will lead to is basically a generalization about the families and the ions that these could form. Everything on this periodic table is a neutral element. There are no ions here, right? So realize that it's only by gaining or losing electrons that an element becomes an ion. And from that information, you should be able to predict the rows or the ions group 13 elements will form. So what kind of a ion or what ion charge would you likely get from everything in group 13? Just to clarify something that kind of turned up in the last chapter, when you're looking at a periodic table, make sure you realize that the horizontal rows, these run all the way across, of course. These are called periods. Why don't I write that? Period. And when you're doing Bohr diagrams, what you're going to notice is that the first period has one shell, second period has 2 shells, 3 shells, 4 shells for the electrons. Make sure when you do Bohr diagrams that you're actually including the electrons in those diagrams. So let's move on. So moving right on to 7.1, 7.2. These are the key ideas. Obviously there's more content than I'm going to throw at you here, but if you had to come right down to the basics, in a nutshell experience, you need to know what compounds are. And compounds are what you get when you have elements bonded together in fixed proportions. This isn't a matter of simply taking, say, an element like, let's pick carbon, and another element like oxygen, and hoping by tossing those two elements up in the air, you're going to get a ratio of 1 carbon atom to 2 oxygen atoms. What you're going to get is a mixture, a mess, different ratios of those 2 elements. A compound will always be in a certain fixed ratio of the elements in the compound. What's going to help you determine how those compounds come together will have an awful lot to do with the number of electrons. And one of the best ways of keeping track of the electrons in the elements in a chemical reaction are by looking at Bohr diagrams. To this point, you've actually had to always draw the number of electrons in the first shell, 2, and then work your way up to a maximum of 8 in each subsequent shell. What you're going to discover as we move through the chemistry section here is that what really matters is the number of electrons in the outer shell. Make sure every time you do a Bohr diagram, you're actually drawing the number of electrons. So finally, when we mention electrons, bonding actually involves electron transfer, which is called ionic bonding, or electron sharing, which is called covalent or molecular bonding. So make sure you're clear as we go through this on the difference between these 2 types of bonding. The ionic, where an electron is transferred, or covalent, where electrons are actually shared. It's important because the actual rules are going to be different for naming compounds and writing formulas. Speaking of rules, rules for writing chemical formulas and for naming ionic compounds are based on these charge balances. In a compound, you're always going to have the sum of the positive and the sum of the negative equal. And yeah, we'll get there. Rules for writing chemical formulas and for naming molecular compounds are based on a prefix system. So you're already familiar with these ionic compounds from last year, where you actually said, okay, copper 2 chloride. Okay, you realize, of course, that I have just abbreviated copper, the symbol in the name. You wouldn't normally do that. I'm just being lazy here, but you would write copper 2 chloride. Copper is a metal, chlorine is a nonmetal. Ionic compounds are combinations of a metal with a nonmetal, something from the left side of the periodic table with something on the right-hand side of the periodic table. In other words, positive ions, that's what the 2 plus means here, combined with negative ions, chlorine. Cl is -1, right? On the other hand, rules for writing chemical formulas of molecular are covalent. And again, molecular is the same as covalent. These are between 2 nonmetals. So in the above example, carbon and oxygen are both on the right-hand side of the periodic table, to the right in particular of the zigzag line. 2 nonmetals are going to share electrons. They're not going to transfer electrons. We're going to have to use a prefix system. In the case of carbon dioxide, notice the di. So somewhere in here you're going to have to learn some prefixes. Di, tri, etc., tetra. Etc., by the way, isn't a prefix. So, the simplest form of matter, as you know, is an element. If it's not on the periodic table, it's not an element. The smallest particle of that element is said to be an atom. Some elements like to combine or bond to form compounds in fixed proportions. That's the definition of a compound. So, sodium chloride, water, these are compounds because you're always going to have a ratio in a compound of, like sodium chloride, of 1 atom of sodium to 1 atom of chlorine. Notice we don't actually write the ones in as subscripts, it's just assumed. Whereas in water, we've got 2 atoms of hydrogen to 1 atom of oxygen. Fixed ratio. Each compound has properties that are different than those of the elements they're composed of. So for example, in, let's say, sodium chloride, NaCl, sodium, poisonous metal, chlorine, poisonous gas. And yet, if you add the chlorine gas to a flask of sodium metal, you're going to get all these little sparks, and at the bottom of your flask, you're going to have plain old table salt. And you can just sprinkle that on your tomato and eat it, no problem. Maybe another example might be something like hydrogen. H2 gas, notice it's diatomic, 2 atoms of hydrogen per molecule. Combine that with an oxygen atom and you have water. And yet hydrogen is an explosive gas. Oxygen supports life. Put the 2 of them together and you wouldn't have life on this planet without water. So for an element, the tendency to bond or form an ion, it's a good word to learn, ion, is determined by the number of electrons in its outermost shell. You know what, that really is one of the most important concepts in this chapter. So I'm going to read it one more time to you. For an element, the tendency to bond or form an ion is determined by the number of electrons in its outermost shell, called the valence shell. So when you see a Bohr diagram, that outer shell is called the valence shell. So take, for example, these 3 Bohr diagrams. Helium, atomic number 2, 2 electrons in its first shell. That's all you can get in that valence shell. On the other hand, neon, noble gas below it, has an atomic number of 10. So you have 2 electrons in the first shell, and you have a maximum of 8 in the outermost shell, or the valence shell. Notice again, argon, another noble gas, 8 electrons in that valence shell. So what that is telling you right off the bat here is that elements with an outer shell that is full or complete. Another way of saying that is a complete octet. Octa means 8, right? Some of you play the piano and you play octaves. An octet is full 8 electrons in the outer shell. And again, that determines a whole lot of the chemical properties. Noble gases really don't react with anything because they're incredibly stable. Everything else on the periodic table is trying to become like them and have 8 electrons in their outer shell. To do that, they're either going to lose electrons or gain electrons or share electrons. You get the point. So Bohr diagrams focus on the valence electrons. Eventually you'll get to the point where you simply record on your Bohr diagram just the valence shells. So atoms tend to acquire the same number of valence electrons as their nearest noble gas. Noble gases, as I just said, have complete valence shells. So neon, of course, has 8 electrons in its outer shell. Fluorine, right next door as a halogen, if you count the electrons here, 1, 2, 3, 4, 5, 6, 7. 7 valence electrons is not the same as 8. So what fluorine wants to do, and I'm using these verbs very loosely here. Obviously fluorine doesn't have any great desire. It's not thinking about it, but there's reasons why it really wants to be stable like neon. So what it's going to do to get 8, it needs to gain 1 electron. And when it gains 1 electron, guess what happens? It becomes a fluorine 1 negative ion. Sodium, on the other hand, notice it has 1 electron in its outer shell, 1 valence electron. So to become stable like its nearest noble gas, neon, it's got to lose that electron. And if you lose something negative like an electron, sodium is going to become a positive ion, Na+1. Right. So an atom and an ion of the same element have completely different properties. And the property difference here is going to be the size. And an example might be simply the realization that sodium atom is larger than the sodium ion. And you can probably reason why. If it's losing this electron, it's going to be smaller. So chemical bonding. Just to repeat what we said earlier, a chemical bond is a force that actually holds atoms together to form compounds. 2 general types, again, ionic and covalent. So ionic bonds involve a transfer of electrons between atoms. We call it ionic bonding. And an example might be something like calcium fluoride. Notice that calcium, again, is a metal. Fluorine is a nonmetal. So ionic compounds are always formed from something on the left side of the periodic table, the metal. And it's always got to come first, combined with the nonmetal on the right-hand side. So what that would look like in terms of an actual diagram, and you know what, you're going to have to be able to draw stuff like that. You show the fact that calcium is giving up its 2 electrons in its outer shell to become a 2+ ion. Now these square brackets, anytime you draw ions as part of Bohr diagrams, make sure you put in the square brackets and then the charge to the right. So once those 2 electrons, one goes to one fluorine atom, one goes to the other fluorine atom, and of course because fluorine has 7 electrons in its outer shell and wants 8, it now has 8 thanks to calcium, and you'd actually have a formula for this calcium F2, which of course is just there, right? On the other hand, totally different type of bonding would be covalent bonding, which involve a sharing of electrons between atoms. The basic unit of a covalently bonded compound is a molecule. Covalent bonds form molecular compounds. Right. And an example of a molecular compound, probably something like oxygen. Notice oxygen is diatomic. What that really means is that in order for oxygen to be stable, notice it's got 2, 4, 6 electrons in its outer shell because it's atomic number 8. 2 in the first shell, 6 in the outer shell or valence shell, and the same thing with another oxygen ion. So the only way it can become stable is to have 8 in its outer shell, and the way it does that is by sharing those 2 from oxygen, 2 from oxygen, and you now have, in a sense, 8 electrons in both of their outer shells. So ionic compounds separate into ions when dissolved in water. Right. And while covalent compounds do not separate into ions, nor do they conduct electricity. If I was doing this in the classroom, at this moment I would grab a big beaker full of water and I would stick an electrode connected to a light bulb into that pure water. And what you would notice is that in the ionic compound, say salt water, the light would come on, whereas in a covalent compound, say sugar water, the light wouldn't come on. Obviously pure water wouldn't come on either. If you like, maybe remind me in class and I'll show you that. So ionic compounds separate into ions when dissolved in water and can conduct electricity, while covalent compounds do not separate into water, nor do they conduct electricity. And again, the reason is a salt crystal. Salt is an ionic compound, so it separates into positive and negative ions, which can actually move from positive to negative electrode and conduct electricity. Whereas a sugar crystal, which is an organic compound, C12H22O11, those are just simply going to separate into the actual molecules. And the molecules are not charged, they're not going to conduct electricity. So you should be able to label the following as either ionic or covalent. And I think we've already looked at this one. Calcium is giving up 2 electrons to form a Ca2 plus ion, and those electrons are going to fluorine. So that would be, of course, dare I say of course, ionic. Whereas this guy is carbon, which has 1, 2, 3, 4 outer shell electrons, and it wants 8. The only way it can get 8 is to have 2 from one oxygen and 2 from another oxygen. It's not giving up those electrons or grabbing them from something else, it's sharing. And when we talk about sharing electrons, we're talking about covalent bonding. What do you think this one is? Got a positive ion and a negative ion. Notice that the positive and the negative ions actually balance. This is a metal, this is a non-metal. You got it. It's got to be ionic. Ionic bonding. Okay, we're now reaching the point where you should actually try to draw a few of these ions yourself. So the one we're looking at here is the nitrogen ions. Start with a nitrogen atom again. Just as it is on a periodic table, you've got atomic number 7. So, how many electrons? It's atomic number 7. We have to have 7 electrons. Get my trusty little pen working here. So 7. How many of these electrons are in the valence shell? Let's see, I see 1, I see 2, I see 3, 4, 5 valence electrons. I don't think nitrogen is happy. Nitrogen wants to have 8. Just an aside here, how many shells would you have needed to draw for nitrogen? Obviously it shows 2, so you know it's 2, but because it's in period 2, the second row, you would know that it needs to have 2 shells, and then you just fill the electrons up from that point. So, in this particular case, how many electrons does nitrogen need in order to complete its valence shell? So, a complete valence shell is 8. It's got 5, so you know that you can add 3 more electrons to it to complete that shell. So you would have to be able to draw a Bohr diagram showing how you would represent these 3 gained electrons. So, and again, they're all going to be ions. So, yeah, you're going to have square brackets around them. And you have to find something that basically is going to donate those 3 electrons. For me, it would be something like aluminum. So, I'm going to draw aluminum. Aluminum is atomic number 13. which basically tells you that you've got 2 electrons in the first shell. This is my abbreviated Bohr diagram. Feel free to do the same. 8 in the next shell, and then in its valence shell, aluminum would have 3 electrons. So those 3 electrons can basically make a 3+ ion. And those 3 electrons, boing, 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 are going to go to nitrogen. So you see, once the 3 electrons, compare this diagram with this guy, now you have a complete octet. That is a stable nitrogen ion, and you have to draw the square brackets around it to show that it's a 3- charge. Where did those 3 electrons come from? Electrons are negative. They had to come from something that donated it. In this particular case, it came from aluminum. We would have a compound called aluminum nitride. And again, that would be just AlN. Your turn. Draw Bohr diagrams below to show how electrons are transferred between an atom of potassium and an atom of fluorine to form ions. This puppy is worth 5 whole marks. If you have any problems, talk to me and we'll try to give you a hand. But make sure you actually read 7.1, 7.2, do the study guide for both those sections, and you will be ready to move on to the tough stuff, the important stuff about ionic and covalent bonding in 7.3 and 7.4. So we started this little presentation with this page. I think now you should be able to actually answer those questions. So it asks you to examine columns 1, 2, 17, 16, and tell me how many electrons each element would lose or gain to have the same number of electrons as its nearest noble gas. So group 1, something like lithium. How many is it going to have to lose or gain? Okay, all of these have 1 valence electron in their outer shell. They want to have the same as the nearest noble gas. The nearest noble gas to something like lithium would be neon. What it's going to do is lose 1. And now it would have the same number of electrons in its valence shell as neon. Group 2, as you might suggest, they're going to form +2 ions by losing 2 electrons. They're 2 valence electrons. Notice I mentioned lithium, but for group 1 it could have been any one of the alkali metals. Group 2 it could be any of the alkaline earth metals. Something different happens, of course, when you get to group 17 and 16. Group 17, the halogens all have 7 electrons in their outer shell. So they want 8. And it's a whole lot easier to gain 1 electron than it is to lose 7. So everything in group 17 is going to gain 1 electron to become 1 negative ions. Everything in group 16, like oxygen, sulfur, etc., if they gain 2 electrons, they are now going to be like the noble gas that's nearest them. So what is the pattern within chemical families? Here it is. Each element within a family has the same number of valence electrons. I mean, I can't write this all on there, but I'll get part of it. Each element in a family, and you might want to add the in a family, has, that's an A, has, okay, that's just a mess, the same number of valence electrons. So, fluorine, chlorine, bromine, all the halogens have 7 valence electrons. All of the elements in group 16 have 6 valence electrons. All of the alkaline earth metals have 2 valence electrons. So what generalization can you make about the families and the ions that could form? Those valence electrons actually determine the characteristics for the family. So everything in those families reacts the same way because of the same number of valence electrons. And given this mess up here, you just know I'm not going to even try to draw that there. If you're not clear on that, talk to me. But okay, so predict the ions group 13 elements will form. Where's group 13? Group 13 is over here, boron, aluminum, gallium, etc. In order to know how many valence electrons each of these has, all you have to do is subtract 10 from these. So 13 minus 10, 3. So all of these will form, 3 plus ions. Get rid of that. And same with group 14, 14 minus 10, all of them will have 4 plus or minus charges. Group 15, 15 minus 10, that means you have 5 valence electrons, and they will probably gain 3 electrons. So that's it, people. That's 7.1, 7.2.